So good afternoon to all. Welcome to this third lecture session of the course, Computational Fluid Dynamics, and course code for the same is MA608. Okay. So already my co-instructor has talked about the overall idea of computational fluid dynamics and also explained you about the different application areas of CFD. Okay. So in this particular lecture, I will first briefly recapitulate about the different scales which are available, and for each of the scale, what are the computational methods which we can employ. Okay, and then I will particularly specify that what will be our stress point in this particular course. And then we will discuss about the physical significance of some of the important mathematical equations. Okay. In terms of scales of simulations, if you see, I have given one plot over here. So in this plot, along the abscissa, I have represented different length scales. So you can see length scale, which is varying very small value of nanometer to large length scales, which are used in the engineering application of up to the range of meters. And time scale I have taken somewhere from femtoseconds to hours. Okay. So when we study our basics of fluid dynamics, we have studied the concept of continuum. Okay. And in terms of continuum, we have seen that we are having some non-dimensional parameter which is called as Knudsen number. If the value of Knudsen number is very small, less than 0.01, then only we consider the assumption of continuum. And if we are having the value of Knudsen number greater than this critical limit, then we have to actually, we cannot assume our medium to be continuous, and we have to consider the individual molecular or atomic activities. Okay. So now you can see that when, and generally if I just recapitulate you the definition of Knudsen number, it is nothing but our mean free path divided by length scale of our physical domain. Okay. So mean free path is nothing but the average distance between the successive collisions. Okay. So now what will be happening when we are having very small Knudsen number? In that case, it means our system size is large in comparison to the molecular length scales. Okay. And similarly, our time domain in which we are studying our properties, these time scales also very large in comparison to the time scales which are associated with the molecular activities. Okay. So under these conditions, what will be happening if we are having certain system which is containing some fluid medium? From that fluid medium, we will be able to perceive some average properties which will be the representative of all the molecular activities which are happening at microscopic level. And as a whole, we will be getting single representative property which will be applicable throughout our entire system. Okay. So that is where our assumption of continuum is valid, and we call our system to be in continuum. Okay. So when we are having continuum, we use our different computational techniques, for example, finite volume method, finite element method, or finite difference method. And generally for the continuum, our length scales are in the range of millimeters to meters, and time scales are in the range of seconds to hours. Okay. And mainly majority of our engineering phenomena lies in these length and time scales. Okay. Then if we go to some system which is having very, very small length scales, less than nanometers, and time scale is very, very small, of the order of 10 to power minus 16 seconds, which is particularly referred to as femtoseconds or picoseconds, then we have to go into the quantum mechanics. Okay. And when we are reaching in the time limits of nanoseconds to microseconds and length scales in the order of nanometers to micrometers, then we have to study the individual molecular activities, and we employ nothing but molecular dynamics for studying such type of systems. Okay, and then we are having a few systems which actually bridges the gap in between our continuum and molecular systems. Okay, so such type of systems are called as mesoscopic systems. So when we are having length and time scale in between the continuum approach and the molecular approach. Okay, so in these mesoscopic modeling techniques, what generally we do, we consider a group of molecules as some fluid particles or fluid parcels. Okay, and instead of studying the individual molecular behavior, actually we study the behavior of these parcels. So obviously these scales will be having requirement in terms of memory less in comparison to the molecular dynamics simulations, because in molecular dynamics we will be studying the behavior of each and every molecule which is there in our system, whereas in mesoscopic modeling techniques we will club group of molecules, we will form these into some fluid parcels, and then we will study the behavior of these fluid parcels. Okay, so some of the techniques which are employed for mesoscopic modeling are smoothed particle hydrodynamics, SPH, then dissipative particle dynamics, Lattice-Boltzmann method, etc. Okay, so this is the general idea of the physical systems which we will be having available in our atmosphere, in our surroundings. But particularly in this course, we will mainly targeting our systems which are in the length scales of engineering range, and continuum assumption is applicable for such type of systems. Okay, so in terms of continuum also we are having a number of other methods which are other than the finite volume, finite element, and finite difference, but in this particular course we will be mainly talking about finite volume method. And before going to the finite volume method, some of the initial concepts we will be introducing with the help of finite difference method. Okay, and wherever required, in order to make the comparison, we will give you some very introductory idea about the finite element method also, but we will not go into much deeper details of finite element method. Okay, so is this point clear about the different scales of simulations? Okay, so now I have not got any response, but I am considering it. Okay, all have understood. Okay, so now let us go a little bit more, start our course. And in this particular case, first I will start with the physical significance of some of the important mathematical terms which are required to analyze our system. Okay, so let me first give you one idea that what we do, we call CFD as nothing but our computational fluid dynamics. Okay, so if you see, it is nothing but a fluid dynamics only, but this computational is an adjective to adjective which is associated with the term fluid dynamics. Okay, and when we study any fluid dynamic system, we are having three different approaches to study that system. So one of the very first approach is theoretical approach, where we solve the governing equations using some analytical methods, using some mathematical approach, and we try to find out the exact solution of the equations. Then we have some another approach that we will be developing some experimental setup. We will be employing certain instruments in our experimental setup, and we will try to experimentally measure the required set of properties. Okay, and third approach is computational approach, where we will be finding the solution of our governing equations using the computational methods. Okay, computational techniques. Okay, so that is particularly we call as nothing but computational fluid dynamics. So what we are doing, basically, we are only studying fluid dynamics, but the approach which we are considering over here, that is actually computational. Okay. So all the that's why all governing laws and equations, all governing laws and equations which are applicable for fluid dynamics, we should know about all these equations. Okay. And while we are actually studying the physical meaning of these equations, because we are not mathematicians, we are engineers, so we should be able to find out the physical meaning which is associated with the mathematical equations. Okay. So while we study the governing equations of our fluid dynamics, so what are the governing equations in fluid dynamics? In fluid dynamics, we have conservation of mass. So conservation of mass is one very, very important equation. Then we have conservation of momentum, and conservation of momentum mainly we derive from Newton's second law of motion. Then if we are talking about heat transfer also associated with our systems, then we have to also find out the conservation of energy, and conservation of energy is mainly associated with the first law of thermodynamics. Okay. So while we will be writing the mathematical form of these different equations, conservation of mass, momentum, and energy, these will be involving some of the mathematical operators, and it is like required to know the physical meaning of these mathematical operators before going into the governing equations and understanding physically that why we are writing governing equation in certain format. Okay. So in this regard, let me now take up one important mathematical term which is called as substantial derivative. Okay. So substantial derivative is one important term which we will be using throughout which we will be using in our governing equations. Okay. So which will be used throughout the course. Okay. So to give you the idea of substantial derivative, let me take up some Cartesian coordinate system. So let us consider I have x, y, z coordinate system over here, and let me consider that I have a fluid element over here. Okay. So I have a fluid element over here, and say this is location number 1 of the fluid element in xyz space. Okay. And let us consider that this fluid element is having certain velocity. So due to its velocity, it is moving, say, from one location to another location, and say it is reaching at some another point in our three-dimensional space. Okay. So this is given as location number 2. Okay. So now what will be happening? Here I'll be having, say, initial coordinates at location number 1 as x1, y1, z1, and the time at which it was in this x1 location, say this time is nothing but t1. And corresponding to location number 2, let us consider x2, y2, z2 as our coordinates and t2 as our time. Okay. Now let us consider that while this fluid element is moving from one location to another location, it is moving in certain flow field, and this flow field is having characteristics that its properties are varying in space. Okay. So it means if I talk about, say, density as one of the fundamental property, so what I am having in this particular spatial location at point 1, say this fluid element is having density ρ1, and while this fluid element is reaching at this second location, it is having density as ρ2. Okay. And what I am saying, that the flow field in which this fluid element is actually moving, this flow field is such that inside this flow field, our properties are actually varying with space and time. Okay. So now I can say that if inside this flow field properties are varying with space and time, I can say that density will be nothing but our function of x, y, z, and t. Okay, so density will be having functional dependence on all the spatial and time parameters. Okay, now if I apply if I now apply Taylor's series, and if I try to find out the density of location number 2 with reference to the density of location number 1, I know that I am having dependence of density on all the space and time parameters. So using the Taylor series expansion, I can say that density at point number 2 will be equal to density at point number 1 plus del rho by del x at point number 1 into x2 minus x1. Okay, so that is something which I am writing from the Taylor series expansion. Then I will be having, because I am having dependence on y also, and y is also changing while our location is shifting from 1 to 2. So I will be having del rho by del x at del rho by del y at point 1 into y2 minus y1, plus I'll be having del rho by del z at point 1 into z2 minus z1 plus del rho by del t at point 1 into t2 minus t1. Okay, so now if you see, I have only considered all the first order terms in this Taylor series expansion. Apart from this, Taylor series will be having some higher order terms also. So I am writing only plus HOT over here. So I am not writing the other higher order terms because we will be neglecting all the higher order terms over here. So I am simply writing over here plus HOT. Okay. Now, if I take this rho 1 to the left hand side, and if I divide throughout by T2 minus T1, I will be finally getting that rho 2 minus rho 1 divided by T2 minus T1 will be equal to del rho by del x at point 1 into x2 minus x1 divided by T2 minus T1 plus del rho by del y at point number 1 into y2 minus y1 divided by T2 minus T1 plus del rho by del z into z2 minus z1 divided by T2 minus T1 plus del rho by del t. Okay, and what I am doing, all the higher order terms I am neglecting over here. So now if you physically see, what is the meaning of rho 2 minus rho 1 by T2 minus T1? So rho 2 minus rho 1 by T2 minus T1 is nothing but it represents the average time rate of change of density field between locations 1 and 2. 1 by T represents time rate, and this we are writing from T2 to T1 and rho 2 to rho 1. So that's why it will be representing the average time rate of change of density field. So left hand side, this particular left hand side represents nothing but average time rate of change of density field. Okay, and you can see over here, this average time rate of change of density field is actually becoming function of del rho by del x, del rho by del y, del rho by del z, and del rho by del t. So it means average time rate of change of the density field actually is a function of all the spatial and spatial coordinates and the time parameter. Okay, now let me take one assumption over here. If I consider that I want to determine the instantaneous time rate of change of density field when the fluid element is passing through point 1 only. Okay, so in that case, what I have to do, I have to take some limiting condition when our T2 is approaching to T1. Okay, so let me repeat once again this point. What I am saying now, instead of finding the average rate of change, I want to find instantaneous time rate of change of density field of the fluid element while it is passing through location number 1. Okay, so in that case, what will be happening? I will be considering that my T2 is tending to T1. Okay, so in that case, what I can do for the left hand side, I can write limit T2 approaches to T1 and rho 2 minus rho 1 divided by T2 minus T1. What it will be? So when we are limiting T2 to T1, it will be becoming nothing but our d rho by dt, where d rho by dt will be instantaneous what will be d rho by dt? It will be nothing but instantaneous time rate of change of density field while fluid element is passing through location 1. Okay, so it will be while fluid element is passing through location 1. Similarly, we will be having, while we are limiting our time t2 to t1, we are having some term x2 minus x1 divided by t2 minus t1. So that will be becoming equal to dx by dt, and dx by dt will be nothing but u direction, x direction velocity. So u, I am saying x direction velocity of the fluid element. Okay, so it will be instantaneous x direction velocity of the fluid element. Similarly, for limit y and z, I can write dy by dt and dz by dt as so here I will be having dy by dt similarly, which I will be writing v, where v represents the velocity of the fluid element in y direction, and dz by dt I will be having as w, which will represent the velocity in z direction. Okay, so if I apply this particular substitution into our main equation, I will be finally finding that left hand side will become d rho by dt, and that will be equal to u times del rho by del x plus v times del rho by del y plus w times del rho by del z, and we will be having one more additional term over here, del rho by del t. Okay, so now you see over here this d rho by dt is something which I have already told you we call as instantaneous time rate of change of the density field of fluid element while it is passing through location 1. Okay, and this is something which we call as substantial derivative. Okay, so this particular term is called as substantial derivative, and this particular term over here is called as convective derivative. Okay, and this del rho by del t is something which is called as nothing but our local derivative. Okay, so this is called as local derivative. So if I say in the vector notation, if I say that my v vector, velocity vector, is equal to u I cap plus v j cap plus w k cap, where u v w are the components of velocity in x y z direction, and I cap, j cap, k cap are nothing but our unit vectors in x y and z direction. Okay, so if I say this thing and we know from our mathematical understanding, mathematical background, that we are having some del operator which is given as I cap del by del x plus j cap del by del y plus k cap del by del z. Okay, so if I apply this formulation, if I now take the dot product of, v vector and del operator, that will be becoming u times del by del x plus v times del by del y plus w times del by del z. Okay, so I am taking the dot product of v dot times del operator. Okay, so from here what will be happening, I will be getting my this equation I can write as d rho by dt substantial derivative equal to this u into del by del x, v into del by del y, and w into del by del z has become nothing but v vector dot delta, and here we are using rho in multiplication, so rho I will be using over here. Okay, and plus I will be having del rho by del t over here. So this is nothing but another way of writing this equation. So in this particular form, we are writing this equation in the vector notation. Okay, now it is very, very important that mathematically we have understood that our substantial derivative, which represents the time rate of change of density field of the fluid element while it is passing through some location, it is actually given as d rho by dt, which is equal to the sum of convective derivative plus local derivative. Okay, but it is very, very important to physically understand that what this really means. Okay, so if you see, the convective derivative represents the variation of the field variable with space, because here you see x, y, z, space coordinates are involved. Okay, and this del rho by del t represents the at given location at point number 1 how our field variable is actually changing with time. So that we call as nothing but our local derivative. Okay, so now if I have to give you one physical example of this one, let me try one example. So what I can do, I can say that, say you are in our campus at IIT Mandi, and it's a very cold winter, and you want to approach the office of some faculty. Okay, you want to discuss something with your faculty mentor, and you are going to his office, and your faculty has actually some heating system in his office, and he has maintained his room completely warm. Okay, so what will be happening, while you will be opening the door and you will be moving from outside into the room, you will be finding that because of the change in location of yours, change of your location, you will be finding that inside you will be feeling some warmer in comparison to outside. Okay, and at the same point of time, say now at the location of the door some hot blower is placed. Okay, so which is throwing some hot air over the person which is entering. So what will be happening, momentarily you will be feeling more amount of warmer, particularly at the location of the door, and once you have entered into the room, then effect of that particular blower will not be coming into picture. Okay, so it means while you are approaching the faculty, while you are entering into the room, you can consider yourself to be a moving fluid element. Okay, so outside you were in the cold environment, and inside the room there were hot environment. So it means with the space our parameters or the temperature field was actually changing. Okay, so it means while you were passing through the door, because at the location of the door, apart from the inside environment, which is basically representing the convective derivative portion, there were momentarily some blower which was supplying hot air also over you. Okay, so it means momentarily you have got some more temperature, and once you have crossed the door, then obviously that momentarily effect of heater or blower will not be coming, but obviously the effect of convective term will be coming, and inside you will be finding more warmer. Okay, so it means substantial derivative represents the total effect of the change in spatial location plus any local transient perturbation which is there in our flow field. Okay, so the way I have represented this particular equation for my density field, in the same way I can represent for any other field, for example my temperature field, pressure field, etc. Okay, now let me also give you the mathematical perspective of this particular substantial derivative. So mathematically, if we see, if I write that my rho is function of x, y, z and time, what I can do, I can write using the chain rule, d rho equal to del rho by del x into dx plus del rho by del y into dy plus del rho by del z into dz plus del rho by del t into dt. Now if I take total derivative d rho by dt, so d rho by dt is actually referred to as nothing but our total derivative. So if I take total derivative, that will be becoming equal to del rho by del x into dx by dt. So dx by dt I can write u plus v times del rho by del y plus w times del rho by del z plus del rho by del t. So mathematically, whatever the total derivative we calculate in our calculus, that total derivative is nothing but equal to the substantial derivative if we try to understand from the physical perspective. Okay, so this is one very, very important term while we will be studying, while we will be studying about the governing equations, we will be finding that this d rho by dt term or this kind of term will be actually appearing many times in our governing equations. Okay, so once we saw this particular equation, we should be immediately able to relate the physical meaning why we are writing this particular kind of mathematical form. Okay, then another important parameter which we will be finding is divergence of velocity field. Okay, so divergence of velocity field is one another important parameter which we will be finding in our almost all the governing equations. Okay, so divergence of velocity field is nothing but del dot v vector. Okay, so to understand this concept, once again let us consider that we are having some moving fluid element. Okay, so we are having some moving fluid element, say it is having volume v and it is having outside surface of this volume as nothing but our s. Okay, now over the control surface I have taken some elemental control surface ds, and this ds is having say normal vector n and it is having some velocity vector v vector. Okay, now what I am saying that this we are having nothing but a very small elemental surface, and over this entire elemental surface we are having velocity vector as v vector. Okay, so now say while this is moving, say I want to see that what is the location of our small this control surface after time delta t. So what will be happening, it is having some velocity v, and after time delta t it will be covering certain amount of distance, and that amount of distance will be equal to nothing but v vector times delta t. So that will be the distance. Okay, and now say this is its new location. So why I am like particularly considering this small elemental surface. So what will be happening if we are considering that our fluid element is moving into a flow field where our flow parameters are changing at different spatial locations. Okay, so it means that density of this fluid element at some location x1, y1, z1 will be different, and some another location x2, y2, z2 it will be different, and some another location say x3, y3, z3 it will be different. Okay, and if we are considering that the mass of this particular fluid element is remaining conserved, the mass of the element is not changing. Okay, or we are saying that whatever the mass with which our fluid element is comprising of, that is having same identity. Okay, so in that case what will be happening, while this fluid element will be moving through the different portions of the flow field, we will be finding that density at different locations is different, so because of which its volume will also be changing. Okay, so this is one very important point. While a fluid element of fixed mass is moving into a flow field which is having variation of the flow properties with space, there our volume of the fluid element will be changing at different locations. Say it is entering into some location where density is high, there it will be shrinking, and if it is entering into some spatial location where we are having low density, there its volume will be expanding. Okay, so it means the volume of the fluid element over here will be a variable parameter. Okay, now what I have done, I have considered a small control surface ds, and say I have considered that this control surface is almost having the uniform velocity field over the entire surface, and it has moved location, it has changed from through distance v bar into delta t. Okay, so now what will be happening, if I see the elemental change in the volume because of the movement of this control surface, so that say I am writing as delta v bar. So let me over here once again make a distinction. When I am writing capital V with arrow sign, that I am referring as velocity vector. Okay, and when I am writing this capital V with a bar sign, I am referring it as nothing but my volume. Okay, so you all of you please take care of this nomenclature. Okay, so now delta V bar I am saying as elemental change of the volume due to the motion of control surface. Okay, so you can see the control surface is having area ds. So ds is the area of the control surface, and its normal vector is having, say, I am writing it as a n cap. N cap represents the normal vector. Okay. And v bar was its velocity, and say we are finding its motion, whatever it has moved through time delta t. So this much distance it will be covering v bar into delta t. So that's why elemental change in volume because of the motion of this small control surface will be v bar into delta t. Okay. So this is my area. This entire term represents area. So area into distance is our formulation of volume. So distance over here I will be having v vector into delta t. Okay. So this is my change in volume when I am actually considering the motion of only small surface. If I have to find out the change in volume of finite element, so I have this entire element of some finite volume V and finite surface area S. So when I was considering the elemental change of the volume because of elemental surface ds, this much I have got. Now if I have to find out the change in volume of finite element, entire element, that will be equal to nothing but surface integral, because over here I have ds term involved. So that will be surface integral ds dot n cap into v vector delta t. Okay, and this I can also write ds into n cap. I can include with dot product of the velocity. So I can write surface integral of velocity vector dot ds vector, because ds into n cap will be our magnitude and direction. That will be our entire surface area vector. And here I will be having delta t as time only. Okay, so this is nothing but my change in volume of the finite element, entire finite element due to its motion. Okay, now what will be happening? So this is the change in volume. If I have to find out change in volume per unit time. Okay, so now what I have to do? I have to find out change in volume per unit time. The change in volume per unit time will be 1 by delta t surface integral of v bar dot ds bar into delta t. So delta t will be cancelling out, and I will be getting finally surface integral of v bar dot ds vector. Okay. Now the surface integral of v bar dot ds vector, if I have to convert it into volumetric integral, how I can convert? I can apply over here my nothing but Gauss divergence theorem. Okay, so if I apply the Gauss divergence theorem, this surface integral I can write as volume integral over the entire volume v bar, and I can write over here divergence of v bar, and this I will be integrating over the entire volume dv. Okay, so now this over here represents the change in volume of fluid element per unit time. Okay, now at this particular location, if I have to apply the principle of substantial derivative for finding change in volume of the moving control volume, so I can say that by taking the definition of substantial derivative, I can say that change in volume of this particular moving fluid element at this location will be equal to nothing but dv bar by dt. Okay, so this point you have to now remember. While we have talked about the substantial derivative, we have actually considered that our fluid element was actually passing through location 1. If we have to consider that fluid element is fixed to location 1, then we only have to consider del v by del t term, local derivative term. But over here we are considering that our entire fluid element is actually passing through this location. So when entire fluid element is moving, in that case we have to consider the total derivative or substantial derivative over here. Okay, so from the definition of substantial derivative, I can say that dv bar by dt is nothing but my time rate of change of the volume at this particular location, and time rate of change of volume at this location I have also determined using this mathematical entity over here while I consider the small elemental surface. Okay, so it means whatever I have obtained over here, that is nothing but equal to the substantial derivative of dv bar by dt. Okay, so let me equate this. So I can write dv bar divided by dt as equal to volume integral divergence of v vector into dv. So while I am writing v, I am writing bar over here. Okay. Yeah, please tell me. Is there any question? Okay, so what I will be now doing, uh, what I'll be now doing. Now let me consider, now what I have done, I am trying to integrate it over the entire surface. So while I'll be integrating over the entire surface, entire volume, obviously in our entire volume, velocity field will not be constant. Okay. So now I will take one assumption that instead of our entire volume V, if I take a infinitesimally small volume element delta V, which is approaching to almost zero. So what I am doing now, instead of integrating it over the entire volume V bar, I am considering a small elemental volume delta V bar, which is almost approaching to zero. So if this volume is approaching to zero, in that case, what will be happening? My velocity field V vector will be almost constant. That will be almost constant over entire delta V bar. Okay, so this is one important point which I am considering over here. So what assumption I am considering, that instead of integrating this right hand side over the entire volume V bar, what I am doing, I am integrating this over some small elemental volume delta V bar, which is so small that it is approaching to zero. So if it's a very small, I can consider that velocity vector over the entire fluid element will be actually constant. Okay. So if I use this assumption, I can write that d by dt of delta V bar, I can write d by dt of delta V bar will be equal to integral over delta V bar, because now my entire fluid elemental volume is actually delta V bar, into divergence of velocity vector into dV bar. Okay. So now, as I have told you that velocity field will be becoming almost constant over the entire element. So I can take this divergence of velocity field outside the integration. So I can write divergence of velocity vector into inside. What will be happening? Inside I'll be having the integration of dv, and that integration I am doing over delta V bar. Okay. So that's why inside I'll be finding delta V bar as my integral. So from here, if I see, I'll be getting divergence of V vector as equal to 1 by delta V bar into d by dt of delta V bar. Okay. So over here you can see that delta V bar is nothing but our elemental volume. Okay. And d by dt of delta V bar represents the time rate of change of elemental volume. Okay. So it means divergence of velocity field physically specifies nothing but the time rate of change of elemental volume per unit elemental volume. Okay. So this is one important significance, physical meaning of the divergence of velocity field. Okay. So from here, let me repeat once again, the physical meaning of divergence of velocity field is nothing but equal to time rate of change of elemental volume per unit volume. Okay. So that is the physical meaning of divergence of velocity field. So now what I will be doing, I will stop at this point, and we will have further discussion on our governing equations in the next lecture. Okay.